Okay, so this is, I told you, the last video, and it probably will be in the TOC that I'm recording. And I mentioned that we're going to go into a little bit more about the history and a little bit more about the alternative versions of the TOC that might be out there. So I think it's very important for you to fully understand this field, where it's coming from, how it got started. And I'm not going to go into too much detail, but I'm going to give you a little bit more background than what I have already. So first off, what you need to know is that in 2001, the U.S. passed what they called the Safe Drinking Water Act. It basically looked at the drinking water that these companies were pumping through your faucet, and it put some standards and regulations in place. And it said, this is what we want to look for. These are the things that we want to report. If any of these get out of whack or out of sync, then we're going to go back and we're going to take a look at what's happening, why is this a problem, and how can we fix it. During this time, we actually see the incorporation of a TOC instrument. The TOC instrument became an alternative to another type of test or test that were done in the laboratory at that time. And those tests were mainly what we called BODs and CODs. BOD stood for biological oxygen demand, and COD stood for chemical oxygen demand. So you can kind of imagine a period of time where a TOC instrument was not in a lab. So how on earth could we go about getting this kind of data without an instrument? Okay, we could do that by hand. And these two methods kind of were in that same field, and it gave us this same kind of data. So biological oxygen demand and chemical oxygen demand were these two methods that were followed in a laboratory back in the day before a TOC analyzer became very common, especially in an environmental laboratory. So these were the options back in the time. No one really wanted to do these. The BODs and the COT test, and some labs still do them. All right, don't get me wrong. Some labs still do them, especially if they don't have a TOC analyzer. But the BODs and the CODs were a pain. Sometimes it would take all day. Literally, folks, it would take all day. There were so many steps involved. There were so many things that you had to keep an eye out on. It was very time dependent in a way. This was a pain in everyone's thorn, or a thorn in everyone's side. No one wanted to do it. So BODs and CODs still exist. There's still methods out there, and chances are we might get you to do a BOD or a COD in our program at some point in time. But TOC has made this arena so much easier and so much better and so much more convenient that we don't have to worry about these kinds of tests again. And that really depends on the lab, and it depends on the types of samples. The U.S. EPA, the Environmental Protection Agency, they basically delivered to us Method 415. Method 415 during that time was a new method that was approved by the EPA to tell you that TOC was approved as an instrument and a method to report these numbers for part per million of organic carbon. So this was kind of the EPA's blessing on the TOC analyzer. We get this method called 415 that comes out of this, and then that method 415 was adapted to across various laboratories in the United States when this became available. So that was very good. It was a step in the right direction. It was a step in automation. It was a step to make my job as an analyst a little bit easier. I could process more samples maybe, and the machine, as long as it was working the proper way, seemed to give me a little bit better data than some of the hand methods with all of the different analysts that were in charge of doing the BOD and the COD test. More history of the TOC analyzer. The TOC was also approved by the USP, and that's something that we've talked about before in this class already. The United States Pharmacopoeia, the European Pharmacopoeia, and the Japanese Pharmacopoeia. The USP, the EP, and the JP all recognize TOC as a required test for purified water and water for injection within a pharmaceutical laboratory. I put also in-betweens, in-betweeners. What does that mean? Well, that means if a pharmaceutical company is making a medication and that production goes through, let's say that they want to switch and they want to do something else and they want to maybe make another medication. How can we ensure that the in-betweens are completely cleaned? Meaning, my new medication that I'm wanting to make, I don't want any traces of the previous one behind to get into that product, right? It has to be as pure as I can get it, and I want to make sure that there's no cross-contamination that's happening. So that's what I call the in-betweeners, and we also talk about water for injection. So if there's a shot and somebody has to give you something, how can we ensure that those liquids are also pure? And all of the water that's used in the manufacturing line, how can we make sure that that is ultra pure as well? So the USP, the EP, the JP, they all recognize TOC as an approved instrument. We can get away with using it without a problem. So therefore, it made its kind of groundwork in the pharmaceutical industry as well as the environmental industry. Another thing I want to mention is that the TOC measures organic carbon. We know this, right? The TOC, total organic carbon. Well, what do these things actually include? What really is organic? We've already talked about some. I mean, we've mentioned like bacteria, we've mentioned disinfection byproducts, right? Because this is how we get our halogens, the fluorines and the chlorines and the bromines that need to be removed. But there's also natural organic matter, and that's abbreviated NOM or NOM. The natural organic matter is just stuff that's there from Mother Nature. Sometimes these compounds are just there due to the plant or the algae growth, the discharge that those things give off. There's a lot of organic types of materials that are related to that, and they're just naturally found in a system. So that is what I would call natural because we did not put it there. It was nothing that was due to us or our activity. But you're also going to find things like detergents and pesticides and fertilizers and chemical runoffs that can also be found in these water sources or in the soil sources that you want to bring in and test. These pesticides, imagine you're a farmer, you're out spraying your crop with all of the pesticides to keep the bugs away. Well, where does that go? Does it just stay on the plant? The answer is no. This can actually be found in runoff. It can actually go through the ground, and it can go maybe make its way into the groundwater. We can see problems everywhere when it concerns this type of material or this type of activity. Fertilizers are the same way. There's natural fertilizers, of course, and there's chemical-based fertilizers that just have a nitrogen source or a phosphorus source in them. But whatever the case is, these fertilizers can stay around. These fertilizers can make their way into the water systems and the soil systems, and then those samples can be brought into the lab and tested to make sure that we are not pumping extra carbon into those resources or maybe into your drinking water as well. Chemical runoffs are another problem. As you can imagine, up and down the Cape Fear River, this is a very important aspect to a chemical manufacturing company because I can set up a huge company and I can discharge some of my waste into that river and allow that to be washed on downstream. Okay, well, chemical runoffs also cause organic type of pollution, and this pollution and this organic activity I can measure with my TOC instrument. So chances are if I go out to the Cape Fear River and I take a sample from there, and I go out to the Greenfield Lake and I take a sample from there, and I go and take my drinking water sample from home, I hope that my drinking water sample tests the most or tests the lowest. It tests the best, okay? I'll have the lowest ppm number there. My Cape Fear River probably going to give me the worst. There's a lot of sludge, there's a lot of nasty, there's a lot of gunk, there's a lot of runoff, there's a lot of discharge that happens in that river system. And my TOC will be able to measure and will be able to report that. As far as modifications go, there's a couple of different things that go on with a TOC analyzer as far as options for you as a user depending on the type of laboratory that you're working in. The first one is what we're going to call high temperature. There is a high temp TOC, and all this time you keep hearing me talk about 680, 680, 680, 680. Well, a high temp TOC analyzer actually heats it up to 1200. So double, pretty much, what the 680 normal standard TOC will do. Catalyst is not needed for this procedure, so those catalyst beads typically are not a requirement. The heat there is enough heat in order to combust all of that material and send it over to carbon dioxide. So that maybe is a positive for you. If you don't want to worry about the catalyst, then this could be a catalyst-free option that's out there. Another option is called photooxidation. And photooxidation, photo is kind of photon. Photon is light, and that basically translates to light doing the oxidation part. So again, in the combustion reaction, think about adding O2 and you are adding oxygen. We can refer to this as the oxidation, okay? So photooxidation uses UV light, and that UV light will oxidize the carbon to produce carbon dioxide. These are good because they're very low maintenance. There's not a lot of pieces and parts and bells and whistles that come along with them. Again, though, the issue is how is your lab structured and what does your lab have approved, and test it to make sure that it works and to make sure it's giving them comparable data. And if they have used or wrote a method on photooxidation TOC, then you might see one. The next one that's on the screen is a UV persulfate TOC instrument. And the UV and the persulfate, it kind of combos both of these ideas together. The UV portion, that is the oxidizer, just like it was up here with the photooxidation, but this time they are adding persulfate to this. And persulfate is just an extra oxidizer. That way they can ensure that they really are oxidizing everything on the inside of that sample. Again, it's very low maintenance. There's not a lot that goes to this instrument. It has a very high sensitivity, but when I say that, it really can't go below a 200 part per billion, which is a 0.2, all right? So our machine can go down to 0.5. And I told you that at 0.5, we don't really go any lower. It's really hard to kind of get everything to stabilize and be consistent after that point. But my 0.2, my 0.5 is kind of the cap. Well, UV persulfate can go a little bit lower because maybe you need to ensure that your sample is ultra pure. So these are what you would find normally in maybe a pharmaceutical type of company where they have to go really, really low and report those values because a standard traditional TOC analyzer is not going to cut it for them. So a UV and a persulfate combo will go lower, and that's the reason it can go lower. It's oxidizing through two different ways, not just through a catalyst bead. Next is a heated persulfate. So as you can imagine, if persulfate was added before in the previous example, it can be added again, and this time heat can be added instead of UV light. So this is a heated furnace type of environment again, and this heated furnace with the persulfate addition is even more sensitive than the previous version. And this can go all the way down to 1 part per billion. And 1 part per billion is 0.001 part per million. Keep in mind, I told you that we stop at 0.5. We don't go any lower than that. This machine, the way that it's set up, can go 0.001. So super, super tiny. The issue here, though, is that the heated persulfate option, as you can imagine, there's a lot of things that go on here, and the reagents carry carbon with it as well. And if you want to go that low, the issue is what kind of reagents are you going to use to ensure that no organic carbon is going to be present. Your reagents and your starting stuff have to be super, super clean if you want this super, super low number. That's the drawback with this. So sensitivity is great. You can go really, really low, but at the same time, you might be investing more money and more trouble in this whole concept of getting things super clean to be used on this machine so it doesn't have any kind of cross contamination or background contamination issues. There's also an option for us with the IC portion. You know, we've talked about total organic carbon, but what about inorganic carbon? This machine does have the capability, if you order the proper attachment, to do inorganic carbon as well. So this measures inorganic carbon in a separate chamber in the TOC instrument, and it normally requires some phosphoric acid in order to work. So with the schematic, this is close to the schematic that we've been seeing. But what you're finding here is an addition. And the addition is all of this stuff up here at the very top. Okay? And all of the other schematics, we've left it off because we've only focused on the total organic aspect. But this instrument, depending on what I purchase, could have a inorganic attachment as well. So this is a separate compartment in a way. If you take a look at the way this is organized, here is a bottle of phosphoric acid, and of course that bottle of sulfuric acid is going to be sucked up into this chamber, and then number 5 from the 8-point valve, right? This is one of the ones that we left off. So that tubing line can actually go into that chamber as well, and my phosphoric acid is going to be in there, and my phosphoric acid and my sample will react, and I can start measuring inorganic carbon. So this sample will eventually be pushed through this backflow attachment, and then it will go into my detector. Eventually it will go into my detector. So this is bypassing the furnace. It's really bypassing the catalyst beads. Again, this is something that we don't really need in order for the inorganic process to happen. So go back and think about the addition of hydrochloric. We said hydrochloric acid is added in the beginning. It purges out all of the inorganic types of carbon that I don't want to measure, and all of that is purged out of the instrument. Well, I do have a modification, and maybe I want to measure that. So that is why this is not going through a combustion tube. That's why it's not going through the furnace. It is in a separate mixing vessel over to the side. It's mixed with phosphoric acid that is getting generated CO2. That CO2 that is getting generated is getting pumped through the instrument, and it goes into my NDIR detector after that. All right, so that's how that process works. Okay, so the next thing is the SSM. The SSM is another attachment that I can purchase for this machine, and this is called a solid sample module. And this is a way that I can bring in a solid sample like dirt and process those dirt samples in ceramic boats. So I basically weigh out those samples and I put them into a ceramic boat. I close the door and it goes into basically a heated oven. And this processing technique will allow me to easily measure organic carbon in solid samples, not just liquid samples. And then finally, we have a TN addition. And the TN addition is total nitrogen content. So this is mainly done for environmental laboratories. The total nitrogen content is an attachment. It processes the sample for total organic carbon, but it also processes the sample for total nitrogen as well. I'm not going to go into the aspect of how that works, but sometimes they do look for nitrogen content area, and my TOC analyzer is able to do that for me. So if you want to see a picture of a TN and a solid sample, well, here's a picture of a solid sample attachment. So the solid sample attachment is going to be right here in the middle, and you can see this labeled as SSM. And that is an attachment that will get my solid samples and eventually feed that over to the TOC instrument that is sitting over on the left-hand side of the screen. And of course, my computer system's over on the right with my software. As far as the total nitrogen goes, there's going to be an external video that I want you to watch, and that external video is going to show you a TOC instrument with a total nitrogen attachment. They're not going to go through how it works, but you are going to see where that attachment is at and how it looks a little bit different. And then they're also going to walk you through some of the software steps in order to enter a sample into the software, get this thing started up, and get it running. So I do want you to watch those external videos. Some of the assignment questions can come from those external videos, so just make sure that you watch them. Take some notes on those too. Just pretend like they're me telling you that information instead of someone else. But that's going to do it for me, all right? So this is where my lecture on the TOC is going to stop. And then you'll probably be required to watch some of these external YouTube videos of TOC theory or people using a TOC instrument, just so that you can see it in action and what they're doing with it and how they operate it. So if you have any questions, you know how to get a hold of me. Keep in mind that all of this material is fair game for a test or a final exam as well, right? So it's the basics of how this TOC instrument is working. So all the pieces and parts that go on the inside and what makes this thing tick. So hopefully at this point you have a better understanding of the TOC analyzer, what its purpose is, what it does for a laboratory, and maybe some pieces and parts that you can routinely maintenance and change out. And then we'll get you into the lab, we'll get you running samples, we'll get you familiar with the software and the instrument on a little bit more personal level. But this is it of the TOC lecture. So good luck on all the assignments. Good luck on the assignment for this part at least. And then make sure you don't skip out on those externals. Those are as important as mine are. So don't skip.